Welcome back, ladies and gentlemen. This is a first lesson of Unit D, Electrical Principles and Technologies. The very first chapter and first lesson that we are going to explore, it's all about static electricity. If you do not know or have not experienced any of a static electricity, you're technically lying because we always use it, and whether it's intended or not, it always exists in our daily life. For example, when you think about the sweater, when you take it off or put it on, you will know that hair's attracted to your sweater, or sometimes you even see a tiny little spark also. Those are the example, and let's explore what static electricity is as we go through. All right, so the very first person who discovered this phenomena of static electricity, which is attraction of multiple matters due to the friction, is Thales Amber. He's in ancient Greek. Around 600 BC, the philosopher Thales found that, and I'm going to highlight this part, rubbing an amber. Amber is a solidified a liquid portion that you see out of a tree sap. If you watch Jurassic Park, basically amber included a mosquito that carries DNA of dinosaur. In any case, found that rubbing an amber attracted some material. In this picture that you see down there, you can see that we have an amber, and amber attracted a feather. By observing the phenomena between amber and feather and how these two materials attract to each other by rubbing against each other, Thales Amber was the very first scientist, even though he was more philosopher, but in the end, ancient Greek time, those boundaries were not that thick. He is one of the first scientists who tested and experimented static electricity. At this point, now you are trying to understand what this static electricity is. It's basically a phenomena where two objects, after rubbing each other, which I like to say friction, they exchange electrons. And electrons exist in every single matter because we learn about this. Every matter is consist of atom. Atom has proton, electron, and neutron. And electrons are the one that can move around. Therefore, if you gain electron, we have negative charge ion. If I lose electron, it becomes positively charged ion, which is also known as cation. And one of the best conditions to make these guys move are rubbing each other. Friction, if you will. If you have a lot of friction, if you want to know, if you have lots of friction, a lot of rubbing, that means heat is generated. If heat is generated, electrons jump from one to another places. Imagine inside of the oven, it's too hot, things try to pop out, something like that. In real life, as you can see, if you have any pet, it's very, very common. Cat is a good example. They like to go inside of any type of boxes. Imagine they went inside a box full of styrofoam like what you see over here. They rub each other, and when the cat comes out, cat will have a bunch of styrofoam attached to their fur. Static electricity's beginning is always about attraction between two matters. So I want you to think about some of the example that you're dealing with in real life related to static electricity. And there are so many different examples that you can think of. Even though there's no right answer or wrong answer in this situation, but it is a good idea to go through some. One of the examples that I can think of is sweater and your hair. When you put those on, put those off. That can be one of them. Another example that you can think of is, have you rubbed your hair with the balloon? For example, this is you with a bunch of hair, and if you have a balloon, if you have bunch of friction happening, so rubbing your hair with the balloon, then there will be attractive force between the two matter, and these two will attach together unless we ground them. Grounding is one of the main terms that you will learn too. Grounding electron means you're basically discharging the electrons. Also, if you walk on carpet in your socks, and if you shake hand with your sibling or your parents, then you're going to give a little bit of shock. You can also feel that on the doorknob too. Those are the examples. Just like a previous example, you can see from the right picture, hair stuck on a sweater is a good example. Also, zapped by the doorknob. And even though I didn't go through the natural phenomena, lightning is also an example. Lightning is an interesting phenomena because it is a friction between water molecule in clouds. Inside of the clouds, we cannot see it, but there are tiny water particles that are clumped together. That's why the colors are really dark when it comes to lightning weather. And because of this friction, there is an exchange of electron happen, and if the electron attract from the clouds to the ground, that's where the lightning happen. We're going to go through that a little bit more detail as time goes. As I mentioned in Unit B, every matter is composed of more than one atom. Atom is the smallest matter that we can think of. Inside of the atom, we have something I like to call subatomic particle. The reason it says subatomic is because it's smaller than atomic. So the first one that we're going to go through is proton. Proton has a positive charge, which you can find it at the center of atom called nucleus. It is heavy and dense. And biggest thing is, cannot move. The second type is called neutron. Neutrons are the one where you can see it over here. It's the one that has zero charge. It doesn't have positive property or negative property. It also can be found at the center of the atom, aka nucleus. The one that you can see from the orbit is called electron. They're the one that has a negative charge. The important property of them is basically they're light, they are movable, or I like to say mobile, and they can move back and forth between the atom to another atom. Now, why did I go through about subatomic particle is because all atoms are not charged. What I mean by that is it's neither positive nor negative. In fact, they're all balanced out. For example, I want you to look at the number of electrons over here. I can see 1, 2, 3, 4, 5, 6 electrons. If you look at the number of proton also, you can see I have 1, 2, 3, 4, 5, and 6. So we have 6 proton. So that means the number of electron, number of proton, they are all balanced. And that is what you see in real life also. Most objects are not charged, they are neutral, because neutral state is basically the most stable part of the nature. This means that they have equal amount of proton, equal amount of electrons. But again, there is a one way that we can make it unbalanced, and that is through the process of static electricity. Basically, an object with more electron than positively charged particle is negatively charged. What I mean by that is this. I want you to look at the sweater on this picture. I'm going to share this simulation with you so you will actually able to see how those interact. But in any case, if you look at the sleeve on the right side over here, positive and negative, they're all balanced. Same thing happened in the middle too. But if you see that the green balloon was rubbing against left side of the sleeve of the sweater, you may notice that electrons actually jump and gathered at the balloon. Electrons move from sweater to the balloon. Now let's think about the total number. I can see that I have 4 proton inside of the green balloon, but I have way more than 4 electrons over here. So theoretically, this balloon has more electrons compared to the sweater that has less electrons now. Remember, conservation of mass, conservation of matter, they cannot be created or just disappear like Thanos' finger snap. They're going from one form to another, or they're conserved in another material. So in this case, you may notice that electron jump from sweater to, oops, there we go. It moved from sweater to the balloon, and balloons are negative charge now. So I'm going to draw that. Balloon, it now has more negative charge, while the sweater, I cannot draw the sweater, this is the best I can do, has now more positively charged. And because of this net positive versus net negative, you should remember our unit B, which is kind of like magnet, opposite attract to each other. I want you to look at this GIF down there. This is static electricity, why there's a zap between a person and the metal doorknob. First of all, the person walk around. By walking around, you have a little rubbing happening between the surface of the shoes and the carpet. Can you see that negative electron jump or move from his clothes to all the way to the carpet, making him positively charged? the red positive. Now the thing is, the door was neutral, but as soon as the person connect their finger or hand, whatever the first part of the body he touched, you will notice that electron jump back to him in this case. Because remember, electrons are attracted by the proton, in this case positive charge, I like to say, over here. So that's where the zap occur. So when an object has more negatively charged particles than positively charged particle, we say that the object has buildup of a static charge. Come to think of it, you may wonder why it is called static. It's because of this. Number one, static, like the word suggests, means it doesn't move. It is stationary. Now that is a bit odd, isn't it? Because I mentioned that electron can move around. Stationary is opposite of moving. So what does that mean? That means charges remain in one area rather than flowing to another place. I'm going to explain to you what that means. So let's go back to our sweater and balloon situation, or wall and balloon situation over here. So I want you to look at, is there any better one? Let's see, there you go. I want you to look at this balloon. So let's say you have rubbing going on between the sweater and balloon. Balloon had more negative charge because electron jump from one to another. Okay, that part is not about static. Afterward it is static. Can you see that electrons stay in a balloon? What I mean by that is, this electron does not go back. That's not how static electricity works. Static electricity, yes, in order to have that electricity, initial part, electron jump from one object to another object by rubbing. However, afterward, what is important is, since electron move one side to another, sweater is now net positive, while balloon is net negative. And because of this positive and negative attraction situation, they decided to stop jumping. They decided to remain in one area rather than flowing to another place. That's why we call this phenomena stationary electricity or static electricity. Not about the mechanism of how that happened, it's about what happens afterward. Obviously, if someone touched that sweater, you're going to be zapped. And that will make neutral part again because another jumping happened. All right, the next one that I'm going to go through is charge separation. A charge separation is, first of all, a negatively or positively, there are two situations. Charged object, when it brought close to neutral object, separation of the charge is what's happening in a neutral object. A big statement, but I'm going to go through each of them using the example down there, and I'm going to draw an example using positive situation because what you see down there is a negatively charged object situation. So first of all, let's go with this neutral metal sphere. Metal is a good matter to discuss in here because it's such a wonderful conductor for electricity, which is no brainer. Let's count how many electrons. I can see 1, 2, 3, 4, 5. 5 electron, 1, 2, 3, 4, 5. 5 protons. So as you may see, it's balanced. Thus, neutral object. No problem in here. Now let's look at how it will behave if I bring a negatively charged metal rod. So imagine I have a metal rod and I rub against with some kind of fur, sweater, or rabbit fur, whatever animal fur, and make it statically charged, something like that. So it remained negative. If I bring it close to this neutral object, what happened is, can you see that our negative charge move away? Because let's think about it. Negative, negative, same charge, they hate each other. They don't want to go separate as far as they can. But positive proton, look what happened. They're rather happy about it. They remain in its place. So there is an attraction happen. It used to be just hanging over here, but as you can see, swing toward the charged rod. But if I don't touch it, if I move it away, then as you can see, it go back to its neutral state. Now let's draw one situation. Imagine on a ceiling, I don't know why, but let's say I put a metal sphere with a thread that is attached at the end. Now, right now we have a neutral metal ball over here. Obviously it's 90-degree because gravity make that metal ball fall or try to fall, so there's no swinging. That's a key point. Now, let's assume that we have a metal rod, but this time it's positively charged. So, through the static electricity rubbing against something, we make this metal rod charge positive. What would happen to electron then? First of all, you will notice that it's gonna swing toward like this. Why that happened is because, first of all, what would this negative charge behave? They will actually go toward or try to be closest to the positive. On the other hand, when it comes to the proton, they just remain whatever the place that they were at. So you may notice electrons try to get close or closer to positively charged object. That's what I like to say. If I bring this rod somewhere else, move it farther away, then what happens is this will swinging back and try to go back to the neutral position. And this phenomena that you can observe in here is what I like to say charge separation, because negative and positive, they used to mingle each other over here, but because of that second object, there is a little bit of separation of the charge occur. And charge separation is so common, ladies and gentlemen. You can actually use comb and your hair also. Rubbing a comb on your hair basically attracts electrons in the paper pieces that move towards the balloon. It is the same phenomena. I have been talking about discharge quite a bit. It is something that you see whenever you touch someone or have a little zap between you and the doorknob. Discharge means a buildup of electricity is finally moved as a bulk, as a group, to another. It's a transfer of the extra electrons. This means that the buildup of charge may be attracted to another object and discharge to that object is happening. So, for example, if I have a rod that is more negatively charged, and if there's someone's hand, oops, I cannot draw a hand. That's too many fingers. Imagine there's a touching occur. Then what happens is these electrons will try to go to hand, and then that's what I like to say, a discharge. A buildup of charge that is attracted to another object. In this case, another object is hand that was neutral. An electron will move to that object. If it's extreme, we call it electric shock. I want you to look at this, well, I forgot this fat cat's name. Garfield, there you go. Garfield cartoon over here. So the first, he gave a little snap to his owner. I forgot the name. But the reason that he was able to do this is because of this action, static electricity, which again happening between his paw and the carpet. And he does that discharge to another pet called OD. And when he was doing the same thing, I think it's more unintentional. This cat just want to have its food. I believe his favorite was lasagna, but right now it's just cat food, which doesn't really matter. But because of that electric buildup, instead of small discharge, it actually gives you a big shock. So that's why pop things happening. Of course, it's exaggerated. But in any case, when it comes to a shock from a doorknob, or in this case, same thing, an animal to another animal, electron basically transfer from the carpet to your body. That's a big part. The second part is this. The excess electrons on your body repels the electron in the doorknob as you get closer. So what I mean by that is, from the GIF, we noticed that a human that walk across the carpet start to have a excess electron, or sometime opposite. This person can be negative charge or positively charged. I think the GIF was more positive, but that one is really don't matter. In this case, it's negative. Whatever the charge that you have either excess electron or absent of electron. In either case, you're going to get zapped. So that part doesn't really matter. It's a 50-50 chance. But in this case, let's assume you have negatively charged, so you have excess electron. Then the door knob that you're dealing with, this is more neutral. So electrons will be attracted by protons inside of the neutral object, which means it like to go there. Charge separation will happen as you get closer. But once you get a contact, or really close distance, then what's going to happen is the sides of the doorknob closest to you become positively charged. So I cannot draw that well, but hand, doorknob will be more positively charged because electrons are going to be more opposite side. That's a lot of electrons. We see a bit of a charge separation. Same thing will happen as you move closer. Electrons in your hands are attracted to positively charged doorknob, which is like my drawing in previous page. And there you go. A discharge will happen. We call it shock. And time to time, you will actually see spark. And this spark may be called an electric discharge. To make yourself understand more, this is a little bit of GIF, except this person has absence of electrons, unlike my written example, and that is okay. Both cases possible. If it's positive, please see that negative electrons are attracted to the doorknob. And boom, there is a transfer of electron. And this is opposite scenario. We call this attraction and repelling between charges, the law of electric charge. The first one is opposite charge attract to each other, just like magnet north and south. Positive, negative, love each other. Negative, positive, love each other. They're meant to be together. On the other hand, like charge hate each other. And same thing goes to negative also. That means if you think about the force wave, they try to be together. On the other hand, same charge, try to go further away. And extreme cases, especially when we're talking about electrons, they can jump between object to an object because they just love each other if it's opposite charge. They can even jump from one object to another object if they hate each other too much. The way that we can generate that static electricity is using Vendograph Generator, which I'm going to call VDG. Vendograph Generator is such an effective building up tool to create electricity. Sadly, this requires demonstration, which we cannot do during online time, so demonstration will be done when you guys come back. We use friction. As you may see, there is a belt, rubber belt, and rubber belt touches this brush. By undergoing this touching, we're actually making this metal head either positively or negatively charged. So this is a little cut diagram, dissection diagram. If you think about how the lightning will be formed, which I can demonstrate to you also, is first of all, the head portion is very positively charged around here. The reason being is because electrons already move from one side to another side. It is attached to one other side, which is a little access tool over here, the second rod that has a negative charge. You may notice that because one side is connected, another side is not connected, but long story short, these two attract because positive and negative attract, thus there is some kind of discharge occur. I demonstrated using my finger too. It's hurt, by the way. The charge build up on sphere and transfer to you when you touch. If you really want to try in school, I will let you try. It's not the most fun experiment, but it does give you a slight shock. Like I said, we cannot do the demonstration, so today we are going to conclude our lesson at this point. The homework part will be solving textbook page 278, Unit D, 123468. When it comes to Unit D, first week of, I don't know when we'll have our first week of Unit D specifically, but we're going to have an exit slip in future, and I'll pick one or two of these guys as one of the exit slip questions.